Okay, so I guess you can all see my slides now. So hello everyone. So I'm Leonardo Banchi from the University of Florence, Firenze, in Italy. I mean, thanks for the introduction. So it's sad that I have to give this talk from home. So I really wanted to be with you, also chatting with you in person. I think it's always a wonderful experience. Family commitments forced me to be here. So I saw a lot of interesting talks, and so I hope that also what I'm presenting is interesting for you. So what I will discuss is about simulating spatial search and state transfer on graphs with long-range interacting quantum systems. The motivation for us was mostly something that is available. So it's mostly coming from physics. So not because of some, I would say, nice mathematical structure, but mostly because these long-range interacting quantum systems are kind of available. They are available, and so they allow us to simulate also different properties of so in graph. And so that's our motivation, was to use the long-range interactions in the system to simulate Grover search and other things. So what I will present is based on the following papers. So my talk is based on the following papers. So most of my talk is based on this paper here. So this paper here, where the main author is Dylan Lewis. So Dylan is a student in Sugato Bose's group from UCL, and he really did an excellent job. So he did most of the things I will present today. And then somehow we'll discuss something more, also to give you some hints about the physics behind all these models. So I will discuss a possible experimental implementation using ion traps, but this would be the second part of the talk. And then as a background, I also give, let's say, this paper that we did with some of the organizers of the conference, so Gabriel and Chris, a few years ago, where you see that somehow that was for state transfer, and somehow it also a background of the slides. I have to say that also so some of the theory behind our findings was inspired by some of the papers already mentioned last week in Jeremy Roland's talk. And so I think I also recommend, if you haven't seen his talk, to look at his talk, and as again as a background. Okay, so let me start then. So the outline of my talk is as follows. So I will start introducing a very basic introduction about spatial search and quantum walks. Assume that all of you is super familiar on this topic. So maybe I would say that perhaps you know these things better than me. And then somehow I will introduce, let's say, the physics-inspired model. So I will introduce what are these long-range interacting models that I will consider. And then I will present some results. And finally, if I have time, and I hope to have enough time, I will also present quickly an experimental proposal with ion traps, also in order to show how we can actually simulate the dynamics of different graphs, with ion traps. Okay, so let's start with the spatial search and quantum walks. So very briefly, assume that you all know these things. So I'm considering Grover search. So Grover search can be defined for, let's say, finding the elements on a database. So here the elements are called, or the index is called X, and it goes from 1 to n. So n is the number of entries in the database. And so what we assume is that we assume to have like a query, like a black box or oracle function f, that somehow, given the input x, returns either 0 or 1, depending on whether x is equal or not equal to the solution that we want. So here in my talk, the solution is marked as this w. So f of w is equal to 1, while f for all the x different than w is equal to 0. So I will assume that there is just one single marked element to keep the discussion simple, but most of the things can be extended with some tricks, I have to say, for more marked sites. So as I think you know, so classically, in order to check whether W is in the database, requires like ON queries, while Grover's algorithm, so Grover's quantum search, can find the solution using just something that scales as the square root of the number of queries, thus giving a polynomial speed up compared to classical methods. But here I'm interested in physical databases. And so what about storing these numbers in a physical database? So that's the main motivation. So again, very quickly, so Grover search is made of two different operations. So the oracle can be written as a unitary operator in the diagonal basis that basically marks, so that basically provides this, this transformation here. And so this effectively marks the solution with a different phase, which is -1. So Grover's algorithm works by repeatedly applying the oracle O and the diffusion operator, which is what is called the G. And so where G is given by this unitary operation here, where S here is the fully coherent state given by the uniform superposition of all the possible inputs. And N here is the number of entries that, I mean, is the number of vertices once you map this into a graph. So the unitary operators O and G can be obtained, let's say, as an evolution with two different Hamiltonians. So O corresponds to the evolution with the Hamiltonian, which is just the, let's say, the diagonal, which is just diagonal, is just a single entry in the W. While G, on the other hand, can be expressed as the evolution with respect to a Hamiltonian, which is equal to the adjacency matrix of the complete graph. So from the physical point of view, this Grover search is like a digital protocol. So it's like a bang-bang evolution with two different Hamiltonians. So at different times, you have to switch on and switch off one of these two Hamiltonians. Okay, so let's again continue with the physics. So now suppose that we have like a physical database. So what do I mean? So consider this example here. So we have like something like this. So we have like 3 spins, something like this. So these are spins. And so this curly edges here refer to a physical interaction between the spins. And so this spin, somehow each spin is like, so I'm focusing on spin 1/2. So each spin is a qubit. So it can have 2 possible basis states. And so 3 qubits have 2 to the 3, namely 8 possible basis states. And so these states can be represented in a graph like this. So like this 0, 0, 0, 0, 1, and so forth. And so one can now map the physical interactions in between the spins, so namely this one here, as a kind of transition between these levels. Now, once we are here, so there are some transitions which are quite easy, something like this. So here we are just flipping 1 spin. Here we are again flipping 1 spin. But here, for instance, we are flipping 2 spins. And what's even worse is that here in blue, so from 0, 0, 0 to 1, 1, 1, we are flipping 3 spins together. Now, interactions like this are less likely in nature. I mean, they can be engineered, but it's more complicated. While on the other hand, like let's say a more simple graph that can be obtained from the interactions is the hypercube here. So where on the other hand, so there is just an edge between the states which differ by just seeing one single spin flip. And I mean, physically, this corresponds like to a magnetic field in the z direction. So you see that somehow once we have like the physics, like these 3 spins, there is no unique way of introducing a graph without doing other assumptions. So the assumption we will do now is to restrict to the single excitation subspace. So what is the single excitation subspace? Well, the name speaks a bit for itself. So we assume that somehow the ground state is 0 and an excitation is just one state 1. So this means that somehow there is just, so all the spins, all the qubits are in the state 0, except for one particular qubit, which is in the state 1. So we can label the states in this Hilbert space via these basis states here, and I can index these basis states with some j. So j runs from 1 to n being the number of vertices, number of entries, and they are given by this tensor product here. So in this example below, now we have a two-dimensional lattice with nearest neighbor interactions. And because of this single excitation subspace, now there is a one-to-one correspondence between the physical, let's say, graph. So the one representing the physical interactions and the one representing the transitions between the different states of the Hilbert space. For spatial search, we are searching for one state that is marked. So in this particular example, so the state marked is the state with label 7, which is also represented in red. And physically, so this marked state can be somehow represented by this marking Hamiltonian. Marking Hamiltonian somehow changes the energy of this local site. So it can be somehow rephrased, so it can be interpreted as a kind of different local potential that is somehow felt by this spin here. So this Grover search from a physical point of view can also be interpreted as a kind of finding an impurity in a system where somehow one spin feels the magnetic field in a different way. So we want an algorithm, of course, that gives us the marked state with high fidelity in an optimal time, because, I mean, something that runs in square root of n is what we know it's achievable from Grover search. We want to do that in a continuous time quantum walk. So very briefly, because again, I assume that you all know these things. So you know that one can define random walks on graph. And so classical continuous time random walks, they are kind of defined like this. So from the graph, you define an adjacency matrix where the entries jk, the off-diagonal entries jk of the matrix are one only if jk are an edge of the graph and zero otherwise. And so one can define a quantum walk via an equation like this, where somehow pj is the probability of finding the excitation in the jth site at time t. And that evolves according to this linear equation where gamma is like a hopping rate, which defines somehow the time scales, and A is the adjacency matrix. So, so we can also do something similar in quantum physics. And so that is what the continuous time quantum walk. So now, instead of the adjacency matrix, we have the Hamiltonian that provides the transition between the different basis states. And the evolution is provided by the Schrödinger equation. So we don't have probabilities here, we have just amplitudes. And so that's somehow also, so the states can be in superposition, and that's also the source of somehow the advantage. Okay, so if we want to solve the spatial search with quantum walk, so it was found by Childs and Goldstone back in 2004, so that one can rephrase the Grover's algorithm as a kind of continuous time quantum walk. So now let's say we have, like, again, W is the marked site, so we have the marking Hamiltonian, and then H is what I call this the quantum walk Hamiltonian. So is a Hamiltonian which is defined from the graph. So H can be, for instance, the adjacency matrix, can be the graph Laplacian. So there are different ways of defining H. And so, for instance, in this paper, I think they used, I mean, everything was the same because they considered just regular graphs. So how does the algorithm work? So we focus on this. Yes, is there a question? Anything? So I assume not. Okay, so please interrupt me if anything is not clear at any moment. Right, so we are focusing here on the search Hamiltonian. So the search Hamiltonian is given by this gamma H. H is the walk Hamiltonian plus the marking Hamiltonian. So we start by preparing the ground state of H, of the walk Hamiltonian. then we evolve the system under, let's say, under the search Hamiltonian for a time t, and such that somehow the system is in state W with a high fidelity. So, I mean, it was shown that basically these continuous time quantum walks take a superpositions of paths. And so interference of those paths lead to finding the marked state quadratically faster than what is possible classically. Right. Okay, so how does this work? I'm going quite slow, so I think I'll do this part more quickly. So let's say for a complete graph, H, so the walk Hamiltonian is given by this quantity here. So the ground state is the S state as before. And so the marked state, W, is the ground state of H marked, and the superposition state is the ground state of H. And the marked state is almost orthogonal to S for large N. And so if we start, and somehow what they found is that as a function of gamma, the ground state psi 0 of H search and the first excited state psi 1 of H search, somehow they have different overlap with S and W. So for small gamma, they have basically large overlap with S. Sorry, I think it's the other way around. Yes. So they have large overlap with W, and sorry, small overlap with W and large overlap with S, and somehow is the opposite here. But for gamma N close to 1, somehow there is a transition. And what happens is that in the large N limit, psi 0 and psi 1, they become like a superposition of S and W. And so what happens is that somehow if we start from S, so this is already mixed with W, and so H can give rise to an interesting dynamics that allows allows basically the state S to oscillate into W and vice versa with the same time. And so the time is given basically by the inverse of this spectral gap, so the difference between the energies, and is given by the square root of n. So So what has been found so far using quantum walks? So in the original paper by Childs and Goldstone, they found basically quantum speedups for high-dimensional graphs, such as the complete graph or the hypercube. They also found advantage for D larger than 4, and this was improved in 2005 by Ambaïnis and Aronson. And then, I mean, it was also extended by Childs and Yi, and recently also by Chakravarti and others for high-dimensional graphs, random graphs, Erdős-Renyi random graphs. So let me now jump into the, let's say, the more physics part. About long-range interacting models. So this was mostly a background. So let's consider the model. So this is the model I will be using in this talk. So this is the walk Hamiltonian. So the walk Hamiltonian is like is what is called an XY Hamiltonian interaction. So this sigma IX is a Pauli operator X acting on the ith side. Which is basically identity everywhere except to the ith side, and one can show that in the NJ so this is a number, a real number, and one can show that in the single excitation basis, so this Hamiltonian becomes very simple. So it's just this Jij, so the interaction matrix, and just that. So what we call long-range interaction. So we are considering one-dimensional systems like a spin chain. And here, for most of my talk, I will be using spin rings. So where somehow the spins are arranged in a ring like this, mostly because the Hamiltonian is easier to diagonalize. And what we call long-range interaction is where basically Jij decreases with the distance as a function of the distance between J and I to the power of alpha. Now, since we somehow we are in a ring, and if we label things like 1, 2, 3, 4, 5, 6, 7, 8, Now somehow we don't know what is the, I mean, the distance between 1 and 8 is smaller than the distance between 1 and 3. And so somehow, I mean, we add also this term here to keep track of the boundary conditions. So, so remember that once we have the J, so we can define also a kind of an adjacency matrix. But here, so the adjacency matrix is provided by these J couplings. And I mean, in the language of graph theory, we have now a weighted graph where the weights are proportional to the distance between I and J to the power of alpha. So even though we have like a one-dimensional system, so this one-dimensional is made less trivial by the fact that all the spins are interacting with all the others, though with some interaction that decreases as a function of the distance. Oh, and now I think that that's the important point. So what was our motivation in the study of this paper? So our motivation is as follows. So for alpha equal to 0, then you see that basically all these numbers here, they are equal to 1. So for alpha equal to 0, we have the complete graph, the full, so it's like a fully connected graph. And so it's like a fully connected spin. And so we know that from the analysis of Childs and Goldstone that we have optimal spatial search where with the time that goes as the square root of n. On the other hand, if we let alpha to infinity, then somehow this model becomes effectively a nearest neighbor interaction. So the qubit is only interacting with the nearest neighbor. And in this case, so one can use bounds from quantum dynamics. So for instance, Lieb-Robinson bound to show that optimal spatial search is not possible. So here we have like an effective light cone. And so the time needed to reach something at distance n is proportional to n. So it's linear in n. So the main motivation for us is like, okay, so now we have a model which, let's say, two interesting limiting behaviors, like a regime where we have optimal spatial search and a regime where we don't have optimal spatial search. So what happens for different values of alpha? I mean, is like alpha equal to 0 like a special point? Is alpha infinity like a special point? Or is there a transition point in the middle where we jump from optimal search to let's say Lieb-Robinson kind of evolution? So that's the main motivation of our study, and also, let's say, the main result I will be presenting in this talk. And also another question is like, whether we can predict the fidelity of spatial search depending on alpha, and also check whether we can achieve this kind of requirements experimentally. Let me show you the results now. So first, we did like some numerical checks. So we tried with alpha equal to 1. And so we basically plotted the optimal time as a function of n, so n being the number of lattice size, the number of entries, the number of vertices, and we found like a perfect square root of n fit, not perfect, but I would say pretty good. And the fidelity was also pretty high, so higher than 95%, and quite surprisingly, at least for me, so this fidelity was increasing rather than decreasing as a function of n. So it was getting better when n was increasing. So how can we somehow explain these results, these numerical results? So first, before the explanation, also let me show you something else. So here we also did other values of alpha. So you see that basically for all the considered alpha here, so from 0.5 to 1.6, then we get some sort of square root of n behavior, at least in this regime here. While, so I would say that here things are getting a bit worse, but I will come back to this point later once we have the theoretical explanation. And also the fidelity that you can see here as a function of n is quite high, let's say, for small alpha, and then it starts decreasing quite significantly in this regime here. So that's the kind of phenomenology that we wanted to explain with some analytical theory. So in order to explain these results, then we used some recent results by Chakrabarty and others. And so according to their paper, so here I'm presenting their paper. So, I mean, I know that some of the authors are in the audience. So please, if I say something which is not precise, correct me if I'm wrong. But according to their paper, so they found the spectral condition, and the spectral condition is as follows. So as long as the gap, that delta is the spectral gap, so the difference between the largest and the second largest eigenvalue of the walk Hamiltonian. So as long as this delta is greater than something that decays with as a function of n according to the inverse of the square root of n. Now, if that's the case, then we can study the spectral parameters SQ, which basically depend on this lambda I. So lambda i's are the eigenvalues of the walk Hamiltonian, normalized in such a way that basically the largest eigenvalue is 1. And so here 1 over n is the number of vertices. Now, the result basically says that if the spectral condition is satisfied, then we have optimal spatial search if and only if the ratio between two of these spectral parameters is a theta 1. So it doesn't scale with n. So how can we? I mean, I will go quite quickly here, or perhaps I mean I will skip this part since I'm quite late and I have also different things to say. Okay, so what does it mean in our case? So remember, we have this the spectral condition. So in our case, we were able to find the spectral gap analytically. And so we found that basically the spectral gap as a function of alpha is given by this quantity. So where n is again the number of vertices, and all these functions like G0 and F, they are functions of alpha, but not functions of n. So using this analytical expansion, we were able to prove that in the asymptotic regime, so where n goes to infinity, the spectral gap scales as n1 minus alpha for alpha larger than 1, and it scales like an O1 for alpha smaller than 1. So if we now plug, let's say, this solution here in the spectral condition, then it's simple to show that basically the spectral condition is always satisfied as long as alpha is smaller than 1.5. And so a numerical, let's say, verification of this result was shown somehow here. So here we have n and the spectral gap, and you see that for alpha equal to 1.3, so the gap, which is this red curve, stays well above to the square root of n, which is this one below. Of course, here we have like a log-log plot. But at the transition point, you see that basically they have kind of the same scaling, while for alpha larger than 1.5, then somehow there is a crossing point, and after a while, somehow the spectral condition is not satisfied anymore. How did we get this result? So basically, we use like the fact that somehow we the adjacency matrix can be diagonalized in a simple way using the Fourier transform. So the eigenvalues can be written as this series here, and this series can be expressed as a function of some special functions, which are the polylogarithm and another function which is called the Lurch transcendent function. So the good things for us is that somehow mathematicians already study these functions, and they have already found some asymptotic expansions. In particular, mathematicians found that basically something like this is true for large n, and there is also like a similar expansion for this other part. So basically, combining all these ingredients being a bit careful, because here we have always powers with, let's say, non-integer exponents. So being a bit careful and doing all this asymptotic analysis, that's how we got the expression for the spectral gap as a function of alpha. So what did we find? So remember that we have this spectral condition, and we proved that the spectral condition is satisfied for as long as alpha is smaller than 1.5, and of course for n going to infinity. And I will show you in the next slide that when n goes to infinity, also the ratio between S1 divided by the square root of S2 converges to a constant value for alpha smaller than 1.5. And so optimal spatial search is proved for alpha smaller than 1.5. So for alpha bigger than 1.5, on the other hand, spatial search cannot exist. And this can be shown using Lieb-Robinson bound, so arguments from the Lieb-Robinson bound. So this means that somehow the alpha equal to 1.5 define like a transition point between a regime where optimal spatial search can be achieved to a regime where optimal spatial search do not exist. So, and the fidelity, so for alpha smaller than 1.5, the fidelity of optimal spatial search can also be obtained analytically. So the fidelity is given by the ratio of these two spectral parameters. Again, doing all the analytical expansions, we end up into this expression here, where, I mean, we keep the dependence on n, because if you remember the numerics from previous slides, the numerics converges quite slowly to the asymptotic regime. And so in order to have a better fit with the numerics, we kept also this leading n-dependent behavior. And so in this expression here also you see that it appears the Riemann zeta function, which is, I mean, has very many nice properties. I mean, asymptotically, we basically find this expression here. Is there a question? I assume not. So asymptotically, we found this expression for the fidelity. So as a function of alpha, so the fidelity behaves like this. So it reaches 1. So we have perfect spatial search for alpha equal to 1. And it basically stays to 1 also for alpha smaller than 1. And then somehow it goes down until it reaches alpha equal to 0, where the fidelity becomes 0. And after here, I mean, it's still 0 because simply we don't have optimal spatial search here. But somehow this defines like I mean, if you come from physics, you realize that here the phenomenology is quite similar to the one of phase transitions, but we are interested here in spatial search, not in phases of matter. Okay, let's get back to the numerics. So now we have all the ingredients to understand numerical results. And so, as you see, basically, so for alpha smaller than 1.5, so we are basically here. Then we have a good agreement with with the theory, and so we have like a very good fit with this square root of n. Here, on the other hand, things start to get a little bit bad, but not too bad. Okay, so that the transfer time is still kind of square root of n, so possibly with some corrections. But the bad part is here. So in the fidelity, you see that in this regime, the fidelity is pretty high. So for smaller values of alpha, and it starts to, I mean, here is still decreasing, but pretty good. But here, on the other hand, things start to deteriorate for two reasons. So the fidelity is going to 0, but also the agreement between the theory and the numerics start to be less accurate. And the reason is that in this regime, the spectral condition is not satisfied anymore. And so we expect some differences with the theory. Okay, so in the final part, so let me also quickly describe the extension to spatial search. I mean, this picture was taken from, again, this paper from Chakraborty. And this extension to spatial search was already considered in their paper for Erdős-Renyi random graph. And so here, that's suppose that we have a tensor as an element of the graph. a receiver as an element of the graph, and we want to transfer one state like this from one end to the other. And then somehow we can start the system into all 0 with the sender in the state psi. And then we can perform an evolution where we have 2, let's say it's like the search Hamiltonian, but with 2 marked sites. So the sender W and the receiver F. And they show that basically here, so one can find, so one can achieve the state transfer in a time which is basically like the square root of n. So I'm quite late, so I will skip this slide. But basically, so in our case, we can basically do the same, but it was a bit tricky to find an analytic expression for the fidelity. So the way we somehow get an analytic expression was to consider a different protocol, which is based on reverse spatial search. So if we find this Hamiltonian HMIs as basically the spatial search Hamiltonian with marked site I, then what we can do is as follows. So we start from W, and then we perform the evolution with the walk Hamiltonian with marked site W. So we know that somehow this evolution maps the state W to the maximally coherent state S with high probability. And if now we apply a different evolution with marked site F, now this state S is mapped into the final state, which is F, which is what we want. So if we now see somehow, if we now believe in this expression, then you see that basically the fidelity is given by the spatial search fidelity square. So if this is O1, then also the other fidelity is O1. We did a bit of numerics, which basically confirmed, even though not perfectly, but kind of confirmed this behavior. So how much time do I have? Is like 5 minutes or?
Yes, around 5 minutes.
Okay, so thank you. So, right. And so again, so we had this, we have these 2 protocols, so the always on versus spatial search, and which both protocols take time, square root of n, and they all have, so let's say, some advantages and disadvantages. So the always on protocol requires some mirror symmetry, but it's actually easier to experiment. It's easier to obtain experimentally. While the other one, it's valid for all the possible graphs, allowing to have like optimal spatial search, and so somehow it's more general. Okay, so in the last few minutes, let me very briefly describe the experimental realization. So we were interested in ion traps. So ion traps, in ion traps, the qubits are basically defined in the states of ions, like ytterbium ions. So using the hyperfine states. And so the effective interactions between the ions are induced by through off-resonant laser beams, which are the one here. And the equilibrium positions of the ions are determined by the trapping potential. And I mean, of course, we have ions, so there is also the Coulomb repulsion. So by finding the minimum of this potential defines the positions in the atoms and then of the ions, and then phonon modes and frequencies can be computed assuming small vibrations around these positions. So, so it turns out that the Hamiltonian in ion trap is exactly what we want, where we have like a Jij, but this Jij is given as a kind of complicated function of this coupling between the qubit and the vibrational modes. And there is also another diagonal term here, which is again given as a complicated function of all these frequencies. Now, so in principle, this Hamiltonian can be written as a matrix. So where you have also a diagonal part. And in principle, I can say, okay, so I have now like a Laplacian with some adjacency matrix given by the off-diagonal elements and degree given by the diagonal elements. So in principle, I can, let's say, perform the evolution according to such Laplacian if I'm able to find, let's say, the experimental parameters in the opposite way. Now, I have to say that this is not so easy, but for long-range interactions, things are a bit easier. And then somehow we found numerically this sort of behavior, which is not a perfect power law, but let's say, pretty good. And so, I mean, we did, let's say, some numerics, and we have shown that basically, so even with the experimental JIJ, so not the perfect power law, we still get pretty high fidelity, which is even higher for smaller alpha. Problem is that actually smaller alpha is a bit more difficult to obtain experimentally because of the coupling between the vibrational modes. So there is a coherent leakage into the vibrational modes. But we found also a way of correcting that using somehow renormalized, let's say, couplings. Okay, so I think I'm close to the end. So I just give you a summary. So we proved that optimal spatial search in long-range interacting spin systems with the interaction decaying as a power law with distance. So optimal spatial search exists for alpha smaller than 1.5. And there is kind of a transition from optimal spatial search to like not optimal search. And we have numerically verified high fidelity spatial search for alpha, let's say, around 1 or smaller than 1. And so we have proposed also a state transfer protocol based on that, capable of routing information in different graphs. And then somehow proposed also an experiment using ion traps. Okay, so with this, I want to thank you for your attention. Thank you.
Thanks for the nice talk.
Thank you.
There is a paper by Ozada, Monroe, Nemoto that they take the two-dimensional lattice and then they add long-range interaction and then they prove searching. How your approach is different from that Ozada et al.
Okay, so first of all, okay, let me try to remember. I don't remember the paper you mentioned, so I cannot really give a precise comment here. But since you mentioned 2D, so in 2D, so first of all, the Lieb-Robinson bound is different. So the exponents you will have for the Lieb-Robinson bound, is it higher or small or lower? I don't remember actually. Yeah, I mean, for sure the transition point will be different. But as far as I know, I mean, please correct me if I'm wrong, but I haven't seen this sort of transitions between these two regimes in other papers. So maybe they did consider a particular value of long-range interactions, and they proved for that value that optimal search is possible. But I don't know that paper. I don't remember that paper, to be honest. So I might be saying not precise things.
Okay, thanks.
Yeah, I have one question, but it's something that I didn't understand well. You were talking at the end, in the last part, you were talking about something about the renormalization of the interaction. I guess you can explain a little more that. That's fine.
Right. So I'm not sure if I heard the question properly. So I think the question was about the last part about the renormalization.
Yes, you talk about the renormalization of the interaction. So do you remember that?
Yes. So about this slide here. So I mean, if you read the previous analysis, then which is basically this one here, then the take-home message from where is that? So the take-home message from where is that? Here. Well, the take-home message from this plots is basically just make alpha smaller, right? And I mean, and this is kind of trivial in some sense because smaller alpha, also you are getting closer to the fully connected graph, so the complete graph. And there you know that optimal search is possible. But there is a problem. And the problem is that, so lower alpha is actually more complicated. And the reason is that, because, I mean, these ion traps, they are not isolated quantum systems. They are also coupled with vibrational modes and then all sorts of experimental imperfections. And what happens is that if you, for instance, consider this plot here, so alpha 0.8, so the probability of leakage towards the vibrational modes somehow is bounded by this quantity, while if you go to alpha 0.2, is bounded by a much larger number. So what happens is that, so for the lower alpha is, so the higher is the probability of let's say leaking out to the vibrational modes. But somehow using some perturbation theory, so we were able to take into account this leakage back into the model. And somehow we found a correction to the couplings that somehow is able to fix, at least for this small time scales, the fidelity. So you see that here, without this correction, so just with the numbers, so the fidelity goes down quite quickly. I mean, it goes to 0.75, not really to 0, but still pretty down. While if implement this, let's say, correction schemes, which is just a renormalization of the couplings based on perturbation theory, then somehow it can stay pretty high. Thank you.